So last time we used our fantasy name generator that's based on a couple simple rules of not having more than 2 vowels in a row and not having more than 2 consonants in a row. And we got 2 out of 5 pronounceable names that were pretty good, but the ones that weren't pronounceable were pretty disastrous. I mean, I'm still trying to figure out how to pronounce this name here. This one, I feel like I'm drunk whenever I try to pronounce it. And this one, I mean, you could use it. I'm not entirely sure what race of character you would assign this name to. So we need to do a little bit better on this, I think. And what we're going to do to make an improvement is change the way we pick our letters. So we're going to come over here to a weighted generator. This is set up the same way as our previous code. We've got the letter class here. I've made one addition where we are keeping track of where that letter is in the alphabet. So each letter here, when it's created, keeps track of is it the 0th letter, is it the first letter, is it the second letter, the third letter within the alphabet. So that's in this self.num counter here. And then we're keeping track of the whole thing with this global variable letter count. We'll see why that's important in just a minute. But our alphabet is set up the same way, A through Z. There's the troublemaker Y that screws up all my logic and my code. But then we're adding in a new list called the probability matrix. This is a list of lists, so it's set up as an array. So basically, the ij element of this matrix is the probability that letter J comes after letter I. So if there's a combination of letters, if there's a permutation of letters, this is permutation, not combinations. If there's a permutation of letters that is more common, it has a higher probability. So for example, A followed by N turns out to be pretty common for names like Brian and Samantha. That's going to have a high probability. But things like, let's go back to our example here, things like X followed by M needs to be a basically 0 probability. It's hard to imagine a name where you're going to have an X followed by an M and it be a satisfying sounding name. And so what we do is we make this a global value. We make, say, a global list. And we start out with an empty list. And here we're just filling in the list with all ones. So all the probabilities initially start out equal as ones. And then what we can do is make exceptions to this, because it's going to be a bit difficult to set up all of them, because we would have 26 squared or 676 entries in the matrix, and we'd have to think about all the names that might possibly contain those permutations. So we'll start out with some obvious ones. So X followed by X should be impossible. So we've got a probability of 23 equal to 0, because X is the 23rd letter in our list that starts at 0. An M followed by a D should be rare. It's not impossible to pronounce, but it should be pretty rare. So we're going to make that a 0.1. So you have to think of this right now as a relative probability, where this is 1/10 the probability of all the others. We shouldn't have any Q followed by R, shouldn't have any X followed by Q, and we just discovered we shouldn't have X followed by M. So let's set that up here. So I would copy this, paste it. I know that X is the 23rd letter in the list. Now I need to go find M. Oh, M I already have here is the 12th letter in the list. That saved me a little bit of work there. Let's see, there's 12. And so this is saying that there's not going to be any XM. In fact, let's go ahead and make the reverse true, that there shouldn't be any MX. So then I just have to flip these two. So the fact that I've had to write that twice is a reminder that this is not a symmetric matrix. So the ij element is not necessarily equal to the ji element. So for example, I should have Q always followed by a U, right? That should be 100% and all the other possibilities should be 0. But that the reverse doesn't necessarily hold, right? I don't necessarily need a Q after every U. That can have, a probability that's spread out. But of course, these aren't giving me real probabilities. These are giving me relative probabilities. So we're going to normalize the probability matrix in this way. First, we're going to fix the spelling of probability. There we go. That's important. Then we're going to actually look over the normalization here. So what we do is we go over each row of the matrix and we total up the total probability for that row. So that's this total value here. Then we just divide every element by that total so that the total probability across any row is going to be 1 or 100%. So given your previous letter, I, your next letter, J, is going to be selected based on this set of probabilities. They're going to add up to 100%. So let's scroll down now and see how we put this probability matrix to use. We're still selecting a random length for the name between 3 and 10 letters. We're still keeping track of previous vowel, previous consonant, etc. But now we've also got to keep track of the previous number associated with the letter. So where it is in the list. Yeah, we're still using our same generator here. We're picking a random letter to begin with, and then we're using this get letter routine. So the thing we have changed now is how get letter works. So if I scroll down here, we now pass an extra argument to this function. So in addition to checking for whether we need a vowel and a consonant, we're also checking for the previous number. What was the previous number that we, or what was the number of the previous letter that we worked with, 0 to 25. So come down here, again, we're importing the alphabet as a global variable. And now instead of picking a random, we're still picking random, excuse me. Now instead of picking a random integer with a uniform distribution, we're picking with it based on the distribution we have set up in the probability matrix. And for that, we're going down to this pick letter. So I've kind of separated the sifting through vowels and consonants with this with calling on the probability matrix. So if we go down to pick letter, we're passing the previous letter's index, list index. We're importing our global probability matrix. And here we're just picking a random number. So here we're picking a random number between 0 and 1. Now remember, our probability matrix is normalized so that all the probabilities are given between 0 and 1. So basically what we do is we look for where this random number R falls in that list of random letters, falls in that list of probabilities. So here we go over the second letter, the next letter J, and we are looking for where it falls in here. So what we're doing is we're taking this value called total, and this is all the probabilities we've looked at so far. So let's suppose our alphabet only had 5 letters in it, and they all had an equal probability. So they each had a 20% chance or 0.2 chance of being selected next. The way this works is it's checking for whether R is less than or equal to the current total. So it's checking for whether it falls within the range of the current letter that we are looking at. And basically what we do is we add the probability on here. So when we come in for the first letter, we're looking for R to be between 0 and 20%. If it's, or 0 and 0.2. If R is not between 0 and 0.2, we have to go on to the next one. So we look for whether it's between 0.2 and 0.4. If it's not in between there, we go between 0.4 and 0.6 and on until we get up to 1. So at some point it has to be chosen, right? And I have a safeguard here just in case something goes wrong. It will print problem. I've done this several dozen times and it's never spat out the problem. So I think my logic is sound here, but just in case, you always want a little error message. And so basically this returns the letter based on this redistributed probability. Now what's important to note is if your entry in the probability matrix is 0, it's never going to pick that letter because it's never going to get to that range within the probability because it's not adding anything to this total, so it's never going to pick that value. So once we finish with that, we spit out the letter that was picked, and then we still have to check for whether it's a consonant or a vowel. So these two can kind of compete with each other and make them run over and over again. Let's run this and see if we get anything significantly better than last time. Let me maximize this. We got sup. That's decent. That's a little bit of an improvement. We got Poncy. That's kind of cool. I like that. It's a good mayor name or something. Eruris. That's better. I know we're not doing Z. Yeah. So for example, I might come across this one and say, okay, so I need X and H to be a forbidden permutation because that doesn't make any sense. So let's copy this one and paste it. So where does H come in here? Let's count up here. 0, 1, 2, 3, 4, 5, 6, 7. So we got 23 and 7 needs to be 0. So this is no XH. And now when I run this, I'm guaranteed not to get XH again. But I end up with VL. So I have to go back and say, okay, I need to set up no VL. So let's look up where V is. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So 21. And 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 for L. Where'd it go? Over here. So now I won't get X. What was I was looking for? VL? Yeah, so now I won't get VL anymore. And so, in principle, and I'm doing finger quotations here that you can't see, all I have to do is run this enough times till I find all the combinations that I don't like or that are unpronounceable and just put those to 0. Or I find the ones that I want to have be rare and adjust those. But that's going to take me forever. Right? Because there are 676 entries in this matrix. I don't have the time or the patience to go through all of that. I might as well just look up pre-established names online at that point. And so the next time we're going to take a look at how we can get the computer to do this for us. And that's where we're going to bring in some machine learning principles to better set up our name generator. So thank you so much for watching. I will see you next time. Bye-bye.